So how about let's get into some material. All right, so now I see there's stuff here on the chat. Let's just try this out. Oh, thanks. Yeah, yeah, no, thank you. You're welcome. I like chat that looks like that. Let's get into some chemistry material. First of all, what is organic chemistry? Organic chemistry is the study of the compounds of carbon. But our agenda for this morning and probably for part of tomorrow is not going to be dealing with uh, uh, organic chemistry per se so much as reviewing topics from Gen Chem, which are important to a preliminary understanding of organic chemistry. So the first thing I'm going to talk about, I'm going to, let's see, I'm going to douse these lights. I don't know where I positioned the camera here is not the greatest. And okay, so let's talk about a review. Hope you can see that, of bonding. I believe that the echo capture on Blackboard will be a much higher quality than the Zoom recording is as far as the number of pixels and the resolution of the image, but that comes with a cost of bandwidth. So one of the tech problems that people experience with the live captures, you simply don't have enough bandwidth to deal with that high resolution camera. I don't know what you're experiencing on your end. But let's talk about review of bonding. Okay, so this is like a Gen Chem thing. Electrons in atoms and in molecules are waves, right? That's the quantum idea, that an electron in an atom or a molecule is a wave, and waves are waves have certain characteristics that are common to all waves, and that is a wave has an amplitude. It goes up and down. It goes up and down, up and down. So we could say that these waves, whether it's a water wave or an electron in an atom, waves are described by a mathematical equation. And we're probably most familiar, maybe depending on how far we've gone in math, with the sine wave, right? And this illustrates the important aspects of a wave that are important for an understanding of chemistry. And if we were to plot this function y is equal to the sine of x, what we would see, and this is typical of every wave, is that a wave has a region of positive deflection. In other words, it goes up, and it has a region of negative deflection. In other words, it goes down. So this wave would maybe look something like this, right? And that's the region of positive deflection. That's the region of negative deflection. That's the region of positive deflection as well. And the positive deflection, that's associated with a positive number, and the negative deflection is associated with a negative number. And if you're positive and then you go to negative, you have to go through zero. So these points here, where the wave function, where the wave function has a value of zero, this is called a node. Okay, and nodes are important because it turns out that the number of nodes is correlated to the energy of the wave. So imagine that's you, and you have and there's a wall, and you are tethered to that wall by tethered to this wall by a string. And let's say you set up a wave in that string. So maybe looking something like this. And you have a node there, a node there, a node there, and a node there. Everywhere where that the wave is equal to 0, where it has neither the positive deflection or the negative deflection, that is where the node is. Now, this situation represents something that you might be doing. Remember back in the days when gyms used to be open, maybe some of you would be working out with those ropes, right? Well, this is a situation of low energy where there are few nodes, right? This is something that you might do on a lazy, hazy, crazy day of summer. Wong, 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 up and down, easy pace. You could do that over and over and over again. Okay, but now let's contrast that to another situation in which there you are, there's your wall, and once again, you are tethered to the wall, but this time instead of wong, 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 a low energy situation where the wave has few nodes, let's say this time you're whoa, lots and lots and lots of nodes, right? That's a much higher energy situation. That's high energy, lots of nodes. And, you know, if you work out in the gym or whatever, you know that this is much harder to maintain than this. So waves have positive deflection, negative deflection. They also have regions where the deflection is neither positive or negative. That's a node. The number of nodes is correlated to the energy of the wave. Okay, so now let's move up to something that looks a lot more like chemistry and a lot less like working out in the gym. And that is that, let's talk about another topic that we're reviewing from Gen Chem, and that is molecular orbital theory. Molecular orbital, MO theory of bonding. Okay, and the molecular orbital theory says that bonds result from the overlap of atomic orbitals, right? And molecular orbitals, we abbreviate that MO. Atomic orbitals are abbreviated AOs, and we're familiar with the atomic orbitals, right? This is like the s orbital, the p orbital, but the hybrid orbitals, the sp3, sp2, and sp orbitals, those are also atomic orbitals. And I guess, and I hope, and I'm praying that you're familiar with what these are, sp2, sp3, sp. And the interaction of atomic orbitals to form a bond, according to the molecular orbital theory, is best illustrated using MO diagrams. Okay, in an MO, so let's look at an MO diagram for the carbon-hydrogen bond, right? Because this is organic chemistry. Organic chemistry is the study of the compounds of carbon. Most organic compounds have lots of carbon-hydrogen bonds. Okay, in this MO diagram, which illustrates the molecular orbital theory, what we do is we have a x-axis, well, we have a y-axis. Let's talk about him first. And this is energy. And so that is we're going to place the atomic orbitals that interact to form molecular orbitals somewhere on this energy diagram. The the hydrogen atom is contributing an electron that resides in its hydrogen 1s orbital. So now remember in Gen Chem, when you were doing electron configuration, you would have, 1s, 2s, 3s. Well, the 1s orbital that hydrogen is coming in with is a very low energy orbital. So I'm going to put that kind of low on my diagram here. That's its energy level, and its representation would be, that's the nucleus. And we know that the hydrogen 1s orbital is spherically symmetrical, right? So so this is just the conventional way of representing the hydrogen 1s orbital. Hydrogen 1s, and there's an electron in here. So I'm going to symbolize that electron by just a line. Okay, carbon is contributing an electron that lives in an sp3 hybrid orbital, let's say. It could be an sp2 or an sp hybrid orbital, but just for the sake of reviewing molecular orbital diagram basics, let's talk about the sp3 orbital. Well, that's a much higher energy orbital. So I'm not going to draw its level here where it matches up with the hydrogen 1s. I'm going to draw it at a higher level because the carbon sp3 hybrid orbital, that is the result of quantum mechanical mixing of the 2s and the 2p, and all of those orbitals are higher energy than the 1s. So it stands to reason that the carbon sp3 hybrid orbital would be a higher energy state. So I'm going to draw that guy up here. So this would be this is where the carbon sp3 hybrid orbital lives. So, okay. And so what does the sp3 hybrid orbital look like? Well, there's the carbon nucleus. And I'm relying on your having seen this picture somewhere in Gen Chem. It kind of looks something like this, except that we traditionally shade one of these lobes. And what does this shading mean? This shading means this is the region of positive algebraic sign, and this is the region of negative algebraic sign, right? These are not charges. It's algebraic sign. We just went through how an electron in a molecule or in an atom is a wave, and a wave has a regions of positive algebraic sign of positive deflection and of negative algebraic sign of negative deflection. And when you go from positive to negative, you go through a node. And so this orbital has a node here. Okay. So you've seen, like if you had a real fancy textbook, you would see this would be maybe blue or green, and this would be a contrasting color. I don't have any of that up here, so I'm just using shading and lack of shading. So, and I'm going to put an electron in there. Okay, a bond results from the overlap of atomic orbitals. So originally this hydrogen and this carbon atom are infinitely far apart. But now I'm going to ram them to within bonding distance. I'm going to ram them to within bonding distance. And so all of these positive numbers, right? Lack of shading represents positive algebraic sign. Shading represents negative algebraic sign. As these two approach together, all of these positive numbers begin adding up to with all of these positive numbers to make even bigger positive numbers. So I could represent the result in the following way. There's the hydrogen nucleus, there's the carbon nucleus. They were originally very far away, but now I've rammed them to within bonding distance. And all of these positive numbers added up to all of the positive numbers on the carbon added up to with all of the positive numbers on the hydrogen to make even more and bigger positive numbers. This is what we mean by the overlap. And let's not forget our little negative algebraic sign lobe over here. This thing would be called a hydrogen 1s carbon sp3 sigma bonding MO. Okay, so what does sigma mean? Sigma means head to head orientation of these orbitals when they got together. What does bonding mean? Well, because remember back in Gen Chem, when you were talking about 1s2, 2s2 and electron configurations, you used the Aufbau principle and Pauli exclusion and Hund's rule to figure out all the electron configurations of an atom, 1s2, 2s2, da, 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 da. And one of the principles there was that the electrons occupy orbitals in order of energy. So this is a low energy situation. It has one node, right? And the more nodes something has, the higher in energy it is. And so this electron and this electron fall into this orbital, and that's why it is called a bonding orbital. But there is also another molecular orbital, because one of the principles that we think is a valid principle is that the number of daughter orbitals must equal the number of parent orbitals, so that we have two parent orbitals. They are interacting to form two daughter orbitals. One of them is this bonding sigma, but there's another one, which is the anti-bonding sigma. Okay, and that is a subtractive combination. So here I added this one to that one and got more and big positive numbers. Now what I'm going to do is I'm going to subtract the carbon orbital from the hydrogen orbital. And that is going to give me an orbital that is higher in energy because it's going to have more nodes, right? So positive hydrogen, so I'm subtracting the hydrogen. This is going to be hydrogen 1s minus this orbital. And so we have the orbital that's going to look something like this. And notice that the shading of the carbon sp3 orbital, that got switched up because now I'm subtracting, right? So these are all positive numbers. When you something minus a positive number is the same as saying plus a negative number. So that's why the shading changed over. And this guy, this would be called a hydrogen 1s carbon sp3 sigma star anti-bonding MO. And it has 2 nodes, right? There are 2 loci of points where you're going from positive to negative, and the more nodes something has, the higher in energy it is. All right. So this is the molecular orbital description of how a bond forms. It's the overlap of atomic orbitals to form these bonds. Okay, so let's do another MO diagram just for fun and practice. And this is again something that I hope you saw in Gen Chem. What happens when a carbon p orbital gets together, interacts side to side? A carbon p orbital interacts side to side with another carbon p. Okay, what would the energy diagram for that look like? Okay, so once again, here we have energy. And we have a carbon 2p orbital. And so we're going to give it this orbital, that level there. And what does a carbon 2p orbital look like? There's the carbon nucleus. A carbon p orbital looks like that, where I've taken care of the shading, right? That's a carbon p orbital. And now this is going to interact side to side with another carbon p. So where am I going to put the second carbon p? Am I going to put it higher in energy or lower in energy? I'm going to put it exactly the same level because these are both carbon p orbitals. So there's my second carbon p orbital. Okay, originally infinitely far apart, and I'm going to ram them to within bonding distance. Because we have two parent orbitals, we need two daughter orbitals. One of them will be bonding, an additive combination, and one of them will be anti-bonding, a subtractive combination. So as I ran these two orbitals closer together, I get, there's the nucleus of one carbon, there's the nucleus of the other carbon, and all of these positive numbers added up to all of these positive numbers to make bigger and more positive numbers. All of these negative numbers down here added up to all of the negative numbers over there to make more and bigger negative numbers. Okay, and so this guy has one node, but it's not an internuclear node. Okay, and so we would call this a carbon p pi, right? What does this pi mean? This means side to side orientation. A carbon-carbon pi bonding MO. Right? And we had an electron there, and they both fell into this lower energy orbital. And then we have the subtractive combination where we're going to take this orbital here on the left, and we're going to subtract it from this orbital over here. And so subtraction just means change the phasing. Okay, and so we see that this guy has two nodes, whereas this orbital only had one. More nodes means higher energy. And we would call this the carbon p pi star anti-bonding MO. Okay, and so I hope this is a review for many of you and that you've seen all of this stuff before. We'll be using the concept of molecular orbitals. I wouldn't say extensively, so that if you feel kind of nervous about what in the world are you talking about, we will use those concepts, but not too extensively, at least not in Orgo 1. So before we take our a break, I want to get to the theory of bonding and the formalism of bonding that we're really going to use a lot, and that is the valence bond theory of bonding. And in the valence bond theory, what we are saying is that we replace, replace the overlap with a line which representing a shared pair of electrons, right? So in the molecular orbital theory, a bond results from the overlap of atomic orbitals, but in the valence bond theory, a bond results from the sharing of electrons between two atoms. And so this is really the approach that we use most extensively. And the fundamental principle here, again, this is a review of Gen Chem, is that atoms most of the time like to have an octet of valence electrons. Atoms like to own or share a total of eight electrons because there's something very stabilizing about having an octet of electrons. And so with that concept, we can come up with what I'm going to present now, which is something that I would like for you either to memorize or even better yet, to understand and to be able to use, because this is really how we represent molecules most of the time. You know, like when you go to the grocery store, you're told that all of the good stuff is where? Along the edges, right? That's where all of the fresh fruit and vegetables are, and maybe the lean meat, and all of the good stuff is along the walls. All of the junk, the carbonated beverages, the ice cream, the potato chips, all of that other stuff is in the middle of the store. Well, for us, it's here in organic chemistry, it's something very similar in that most of the time, most of the atoms that we're going to be interested in lie along the edges of the periodic table. So you probably haven't memorized the periodic table, but for example, something like a technetium, Tc, right? That's kind of in the middle of the periodic table. We won't be talking about technetium, right? We'll just be talking about most of the time about selected atoms that tend to live along the fringes of the periodic table. And so what I'd like to do is present a little chart that I would like for you either to memorize or understand and definitely be able to use about the common valencies of the atoms that are most important for organic chemistry. Okay, so X. So don't go looking for element X on the periodic table. X is just a generic placeholder that represents the halogens, right? And I use this a lot. The halogens tend to react and have properties that are very similar one to the other. So this X, that means fluorine, chlorine, bromine, or iodine, right? So that's one of our important elements for organic chemistry. And when a halogen is in an organic molecule, it can have a charge or it could be neutral. Most of the time in this course, we are not going to be dealing with anything that has more than one positive charge or more than one negative charge on an atom. You know, in Gen Chem, you're dealing with something like zinc 2+, where the zinc atom has two positive charges on it. That's not going to be a common situation for us at all. So most of the time we're going to be dealing with atoms that have either +1, -1, or they're 0. And when a halogen has a -1 charge and an octet of valence electrons, that will be its charge. It has 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's a halogen with 8 electrons. When it's surrounded by 8 electrons, and it is going to have this negative charge. And how many bonds is this forming? 0, right? So this would be something like Cl- or Br- or I-, familiar to us from Gen Chem. It forms 0 bonds, 0 covalent bonds. It might have an ionic bond, but it's not going to be a covalent bond. But the halogen can also be neutral. It can have 8 electrons, 1, 2, 3, 4, 5, 6, owning 6 and sharing 2 with another atom in a covalent bond. So this halogen is owning 6, sharing 2 for a total of 8. It's happy, it has the octet rule, and it is forming 1 bond. Okay, but halogen can also have a positive 1 charge and an octet of valence electrons. So a situation where that could accrue would be, there's our halogen. It's owning 4. It's owning 4 and sharing 4 for a total of 8. But in this case, it must have a positive charge. Okay, so when halogen has an octet and a positive charge, it forms 2 bonds, but it doesn't have to be 2 single bonds. It could be a double bond as well. Okay, so a couple of notes about this first entry in this table. And that is, in Gen Chem, whenever you draw an ion, they probably told you to write it in brackets with a superscript. That was then, and this is now. This is not how we write a charged species in organic chemists for use by an organic chemist. If the atom has a charge on it, the charge is written right close by the atom that bears the charge, and we dispense with brackets, right? Writing ions in brackets, that's Gen Chem, right? That was then, this is now. We don't do that. This is what we do. If the atom needs a charge, you write the atom, you write the charge close to the atom that requires it. Okay, so let's keep going. Oxygen is the next important element for organic chemistry. And oxygen, when oxygen has an octet, when it is owning or sharing a total of 8 electrons, it again could be either negative, neutral, or positive, depending on how many bonds it is formed. Okay, so oxygen, when oxygen has an octet and a negative charge, it is forming 1 bond to something else, 1 covalent bond to something else. So this could be like the oxygen atom in hydroxide, OH minus. It is owning 6 electrons and sharing 2 with a hydrogen over here. Okay, when oxygen is neutral, it forms how many bonds? 2, right? Water, H2O. There's the oxygen atom forming 2 bonds, and it has 2 unshared pairs of electrons, it owning 4, sharing 4 for a total of 8. But just like we saw with this halogen, it doesn't have to be 2 single bonds. It could also be a double bond. It's still 2 bonds. Excuse me. Okay, now oxygen can have an octet. Most atoms like to have an octet. Oxygen has an octet. And when it does so and has a positive charge to boot, it is forming 3 bonds, right? So this is like the hydronium ion, so familiar to us from Gen Chem, H3O+. But again, it doesn't have to be 3 single bonds. It could be a double bond and a single bond. That's still 3 bonds. And when oxygen has an octet and a positive charge, it forms 3 bonds. Or it could even be a triple bond. So all of these oxygen atoms, they all have an octet of valence electrons, but they also have a positive charge. And so they are forming 3 bonds. So maybe you've detected a pattern here. For halogen, when it's positive, when it's negative, 0 bonds. For oxygen, when it's negative, 1 bond. The next atom is going to be nitrogen. How many bonds do you think negative nitrogen is going to form? 0, 1. Oh, this is going to be 2. And what was the pattern up here? When halogen was neutral, it formed 1 bond. When oxygen was neutral, it formed 2 bonds. When nitrogen is neutral, how many bonds is it going to form? That's going to be 3. When halogen was positive, it formed 2 bonds. When oxygen was positive, it formed 3 bonds. When nitrogen is positive, how many bonds is it going to form? It's going to form 4, right? So there's a pattern going on here. So nitrogen that with an octet, nitrogen with an octet is going to form 2 bonds. And when nitrogen forms 2 bonds, it has to have a negative charge, but it doesn't have to be two. It doesn't have to be 2 single bonds. It could be either a double bond or 2 single bonds. However you cut it, it's still nitrogen with 2 bonds. When nitrogen is neutral, it's going to form 3 bonds, but it doesn't have to be 3 single bonds. It could be a double bond and a single bond, or it could be a triple bond. When nitrogen is positively charged, it's going to form 2, 3, 4 bonds, right? There's a pattern going on here. But it doesn't have to be 4 single bonds. It could be 2 double bonds. That's still 4 bonds. Or it could be 2 single bonds and a double bond. It's still 4 bonds. Or it could be a single bond and a triple bond. It's still 4 bonds. So these are all of the various combinations in which the nitrogen that has an octet can exist. Okay, so need next to talk about carbon and hydrogen, but let's take a 10-minute break now. And at 10 o'clock, at about 10 o'clock, we will resume. In the meanwhile, maybe if you have a question about anything, you can chat. You can send me a chat. So let's take a short break. Maybe at around 10 o'clock, we'll resume. Anyone have any questions for me about anything?
Dr. Rubio?
Yes.
There's still some students who are having trouble accessing the Echo Live.
Okay, what would the problem be? Are they clicking on the right stuff?
Yeah, it sounds like they're like clicking on the right buttons, but the message they're receiving is that the link is unavailable. So like when you and I click on Echo Recording, it goes to like the list of the dates and the class name, but they're not even getting to that list, so they're never seeing the live button.
Could you go to that page and somewhere, like I think in the top left, sorry, top right, do you see a button that says Start Capture?
Let's see. I do not see that.
There in the upper right, it says Start Capture. No?
So are you asking after I click the live stream or before?
Before. You get a big menu of like all of the lectures that I've scheduled.
Right.
And in the upper right, do you see a button that says Start Capture?
I do not.
Okay, well, you know, because I used this last semester, I didn't have to press anything. It was all set up. Anybody there not having trouble with the Echo recording?
So I went into the student view, and when I click on it in the student view, it says that the course link is not available. And
Okay, well, I don't know why that is. So I'll just have to look in look into it. Does it say it's recording?
So on my end, when I'm in the instructor view, I can see that it's recording and that you have live, live
When
video.
you're in the instructor view, do you see a button that says start capture?
No, that's what I don't see.
Okay. Link is unavailable. Yeah, I don't know. Maybe that's my fault. Maybe I was supposed to press something because I used this last semester and I didn't have to press anything. It was just automatically there. I'll have to look into it. Hey, it's the first day of school, right?
Mhm.
So trying to figure out, anybody out there, can you send a message, or anybody out there not having trouble with the echo recording? Oh, so I'm going to take a short break. Oh, what's this? I'm having the same issue with the live capture, the echo live capture, right? Okay, I'll have to figure out what's going on there. I didn't think I had to do anything, but maybe I do. Okay, so we'll figure it out for next time. Well, I guess I'm glad I brought my Zoom. I'll be right back. Okay, folks, so let's continue talking about the common valencies of the various atoms that are important for organic chemistry. Um, I realize that some people are having tech issues. We'll try to figure that out so that it can be run a little bit more smoothly. All right, so we're talking about the common valencies of the various atoms that are important for organic chemistry. And now we did halogen, oxygen, and nitrogen, and now we've come down to the star of the show, which is carbon. All right, and so just like for all of the other elements, carbon, when it has an octet, can have either a -1, a 0, or a +1 charge. So when carbon has an octet and a -1 charge, it is owning 2 electrons and sharing 6 electrons for a total of 8. And it will have this -1 charge. But just like we saw with some of these other elements, it doesn't have to be 3 single bonds. It can be a double bond and a single bond for a total of 3 bonds, or it could be a triple bond for a total of 3 bonds. Okay, so carbon with a negative charge can look like that. When carbon is neutral, it's going to form 4 bonds. And it doesn't have to be 4 single bonds. It can be 2 double bonds, or it can be a single bond and a double bond and another single bond, or it could be a triple bond and a single bond. So however you cut it, it's still 4 bonds. All right. Now, what about carbon with a +1 charge and an octet of valence electrons? Not possible. Now, that doesn't mean that carbon can't have a positive charge. It does, but when carbon has a positive charge, it can't have an octet. Not possible if carbon has an octet. If we look at this pattern here, we see halogen was positive with 2 bonds, 2 bonds, 3 bonds, 4 bonds. This should be 5 bonds. But one of the things that we have to get straight right away is that carbon can't form 5 bonds, because 5 bonds would mean sharing 10 electrons, and the octet of the octet of carbon has been exceeded. Okay, so that's the table for carbon. All right, so now the next atom that is important, and this will be the last one on our little valence table, will be hydrogen. And so hydrogen kind of breaks all of these rules because of its position on the periodic table, is that hydrogen, first of all, doesn't need an octet. It's happy with a duet of valence electrons. And hydrogen has a negative charge when it is owning 2 electrons. This is the hydride ion. When hydrogen has a duet of valence electrons and it's neutral, it is forming 1 bond. And when hydrogen has, and hydrogen can also be positively charged, we see this all the time, that's the proton. So hydrogen doesn't fit into this nice little scheme that most of these other elements do. It's kind of on its own. Okay, let's talk about the breakdown of the octet rule, because everything that we've said up to this point has dealt with the octet rule, and everything on this table that I presented is predicated on the atom having an octet of valence electrons. But we see situations where the octet rule breaks down and where the atom doesn't have an octet. Okay, so first exception, right? And we're not ready to talk about any of this stuff in any kind of detail right now. I just want to put all this down for the record. The carbocation is a carbocation, is a carbon atom that has a positive charge, but this just has a sextet of valence electrons. It doesn't have an octet. An octet of valence electrons on carbon and a positive charge to boot, that's impossible, right? But we see positively charged carbon, and we'll see this quite extensively, but it will always be an electron deficient carbon with only a sextet of valence electrons. Okay, another breakdown that we'll meet later in the semester will be that of a so-called radical. A radical has a septet of valence electrons, and we could have a carbon-centered radical that is sharing 6 electrons in 3 bonds, and it has a lone electron rather than an electron pair. And these radicals, they have a septet of valence electrons. So let me ask you a question. Do you think you can go to Chemicals R Us and buy a bottle of carbocation? Do you think you can go to Chemicals R Us and buy a bottle of radical? Oh, these are very unstable, very reactive species. Atoms want to have an octet. That's what this whole table is all about. What does an atom look like when it has an octet of valence electrons? But there are situations where the atom doesn't have or won't have an octet of valence electrons, and it will be unstable and pretty reactive. The third and final category of breakdown here would be electron deficient species, such as a molecule we'll be talking about quite a bit, borane, BH3. If you look at the position of boron in the periodic table, you see that boron is group 3. It is contributing 1 electron to each of these bonds to hydrogen, and it can only form 3 bonds with the number of electrons that it brings in. So there are situations where the electron, where the octet rule breaks down. Okay, so now let's review. Try to go to this format instead. So let's review another Gen Chem concept very important for organic chemistry, and that is the formal charge. So when I was presenting this table here, you see how I put the charges here, and I made the point that in Gen Chem you were told to write everything in a bracket with a superscripted charge, and how that was then, but this is now, and we don't do that for organic chemistry. So where did all of these charges come from? So that is the calculation of the formal charge. All right, so let's review how to calculate a formal charge. The formal charge on an atom, right? And we calculate the formal charge for every atom. The formal charge on an atom is equal to the good old-fashioned Roman numeral group number of that atom. So You know about Roman numerals, right? Like Super Bowl XXXVIII, right? That's a Roman numeral. And you know how in the periodic table, each atom is columns of the periodic table are associated with a Roman numeral group number. So that's what I'm talking about here. Formal charge on an atom is the Roman numeral group number of that atom minus the number of bonds to that atom minus the number of unshared electrons on that atom. So it's the application of this formula. That's where all of these charges on this table came from. Okay, so example, something like this. All right, so this guy here, we see that oxygen is group 6. 6 minus 3 bonds is 3. 3 minus 2 unshared electrons is 1. So when oxygen forms 3 bonds and has an octet of valence electrons, it must have a positive charge, right? That's where we got this number from. When oxygen forms 3 bonds and has an octet, it has a positive charge on it. Okay, so now this structure here is this structure here provides an entree into another convention that is observed in organic chemistry that you probably didn't do in Gen Chem, and that is the very annoying but time-saving convention that showing formal charge is mandatory, comma, but showing unshared electrons is optional. Okay, so let me see. Someone's complaining about me. What's more difficult when he moves away from the computer? Anum, what's more difficult when I move away from the computer?
I'm having a hard time hearing you when you're moving away from the computer.
I'm supposed to be on a mic. Okay, all right. Thanks for telling me. I guess I'll just stay here. All right, so showing formal charge is mandatory, but showing unshared electrons is optional. All right, so let's put this valence table in action, right? So let's do some problems where we're using that valence table. And remember, I asked you to memorize that table, be able to understand that, that table, and let's be able to use it. Okay, what if I were to ask you to draw the Lewis structure of ozone, O3. Okay, and let's make sure that we realize that ozone is 3 oxygen atoms in a row. It's not a triangle of oxygen atoms. It's 3 oxygen atoms in a row. Boom, boom, boom. Okay, so there's our skeleton, right? 3 oxygen atoms in a row. And we know that most atoms like to have an octet most of the time. There are exceptions to when to the octet rule, but let's just not think about those for a while, right? Most atoms like to have an octet. Let's just go with that. Okay, so now this oxygen atom here, I want it to have an octet, so maybe I could do something like this. 1, 2, 3, 4, 5, 6. So this is oxygen with an octet. It is forming 1 bond, and that an oxygen with an octet that is forming 1 bond, that must have a -1 formal charge. Was that on our table? Was that on our table? Oh, heck yes, here it is. Okay, what about this oxygen in the middle? We also want him to have an octet. He already has 2 bonds here, but when oxygen is neutral, it is forming 2 bonds. And so to come up with the Lewis structure for O3, where the overall charge is going to be it's going to be neutral, right? Because ozone is O3. It's not O3 minus. It's not O3 plus. It's O3 zero. So if we're going to make this oxygen in the middle neutral, this oxygen here is going to have to be positive. And positively charged oxygen forms 3 bonds. That's what our valency table was saying. 1, 2, 3. And then it has an octet. Oh, this is wrong. This can't be right, because on our valency table, we never saw an oxygen that is forming 4 bonds. Oxygen can form 1 bond, 2 bonds, or 3 bonds, but not 4. So this couldn't possibly be the correct structure of ozone. So let's try again. Oxygen, make this guy neutral, make this guy negative, forming 1 bond. This oxygen in the middle, let's make him positive, forming 3 bonds. And this oxygen over here, forming 2 bonds and being neutral. Now that is the correct structure. See, this is how you're using the valency table, is that each atom forms when it has an octet, forms a characteristic number of bonds, and your job is to figure out how the atoms are strung together in such a way that the charge comes out right. Here, this overall charge had to be neutral, and that the number of bonds come out right. Each atom forms a characteristic number of bonds when it has an octet and has a certain charge. Okay, so let's try this again. Another problem. How about draw the Lewis structure of N3 minus, and this is 3 nitrogens in a row. It's not a triangle of nitrogen atoms. It's 3 nitrogen atoms in a row, right? And everything is going to have an octet, and it's going to have to work out that the overall charge of the species is -1, but everything has to form a characteristic number of bonds. Okay, so maybe let's look at some stuff that would be wrong. All right, so that's going to be our basic skeleton, right? 3 nitrogen atoms in a row. We know there has to be at least a single bond somewhere. And maybe let's put, does nitrogen ever form one bond? Does nitrogen ever form one bond? If we look back at this table here, nitrogen is forming 2, nitrogen is forming 3, nitrogen is forming 4. Does nitrogen ever form one bond? No. So we have to give this at least a double bond. Okay, and so when nitrogen has an octet and forms 2 bonds, that has to be negative. Okay, what about this nitrogen in the middle? Okay, here's that nitrogen forming 3 bonds. Is that allowed? It is. And when nitrogen forms 3 bonds and has an octet, it is neutral. And so to make the Lewis structure of N3 minus, we found a negative charge. This guy has to be neutral. But when nitrogen is neutral, it forms 3 bonds, right? So there's 1. We would have to do this, and nitrogen never forms 5 bonds, right? So this is wrong. So what is correct would be, how about a nitrogen with 2 bonds, a nitrogen with 4 bonds, that's going to be positive, and over here, a nitrogen with 2 bonds. And so the overall charge on this species is -1. Everything has an octet, and all of these nitrogen atoms are forming a number of bonds that are consistent with that valency table of characteristic bonds. Okay, so now I'm going to rock your world now, and I don't mean that in a good way. Is that I made the point that writing the formal charge is required, but writing unshared electrons is totally optional on the part of whoever is writing the Lewis structure. So maybe in Gen Chem you always drew unshared electrons, but that was then and this is now. An equally valid Lewis structure for this guy would be, believe it or not, something that looks like this, where the electrons, unshared electron pairs, are not represented. They're totally optional on the part of whoever is writing the Lewis structure, but the charge is never optional. It must always be written. So I don't never have to write an unshared electron pair, but you need to know whether any are there and how many there are there. And how are you going to know? Because you know that most atoms like to have an octet of electrons. So on this oxygen atom here, I didn't write any unshared pairs of electrons. Does that mean there aren't any there? Not at all. Because we know that atoms like to have an octet. This line represents 2 electrons. This guy must have 6. The thing I'm trying to put across here is that writing unshared pairs is optional, but writing the formal charge is mandatory. What about this guy? Another equally good way of writing this Lewis structure would be just to dispense with all of the unshared pairs of electrons, but we can never dispense with the formal charges. And once again, I didn't write any unshared electrons on this nitrogen. That doesn't mean there aren't any there. There are 4 unshared electrons on this nitrogen. But I just am assuming that everything has an octet because that's what atoms like to do. Okay, so this is an important thing to keep in mind, is that the unshared pairs of electrons, that's totally optional, but the charge is never optional. So now let's get into something that looks like a lot more like organic chemistry, and that is drawing organic molecules, how to represent them, how to draw them. Drawing organic molecules. So one of the things that becomes very apparent pretty quick in organic chemistry is that organic molecules have lots of atoms and lots of bonds. So let me try to show you a picture here. I hope this works. Okay, what am I going for here? Okay, here. So hope you can see that on the Zoom. And so this is a molecule of fentanyl. Anybody know what fentanyl is? Do you know what that's used for? Yeah, that is a surgical anesthetic. It's also a, what's this? 100 times more potent than heroin. Pain management. Yeah, opioid drug. Exactly. Yeah, this is a surgical anesthetic. And if you look at this molecule, you'll see there are lots and lots of atoms, lots and lots of bonds. If we had to draw every atom and every bond, we would never, ever have time to talk about the chemistry of fentanyl, right? We would be spending all of our time drawing the molecule and drawing all of these atoms and drawing all of these bonds. So what we need to do is come up with short and efficient ways of representing organic molecules, many of which are going to be big molecules. Okay, so now, how do I get rid of all of you guys? This, here. Okay, I'm trying to get rid of this bar up here. I forgot how to do that. Oh dear, so many controls here. No? Oh well, forget about it. Okay. So there are a couple of different ways of representing on, what's this? Sorry, I'm just trying to clean up the screen. Oh, thank God. All right, so there are a couple of different ways of representing an organic molecule. First, there's the so-called full Lewis structure. And in a full Lewis structure, we show every atom and every bond. Okay, so I'm going to demonstrate the differences between the various ways of drawing an organic molecule. I'm going to I'm going to demonstrate using a molecule of guess it's called geraniol. Geraniol, right? This is the molecule that's responsible for the delightful aroma and fragrance of a geranium. Okay, so I'm going to draw the full Lewis structure of geranium. Okay, so there's a carbon, there's a hydrogen bonded to a carbon. Carbon forms 4 bonds, so it looks like this. And then we have a carbon that's bonded to another carbon, maybe looking like that. And then this carbon here has a double bond. And then there's a carbon over here with a hydrogen there. Oh, my hand's getting so tired. And then another C, and then another carbon with 2 hydrogens. Wow, my hand's starting to hurt now. And then there's another single bond here to another carbon, and then carbon up here with 4 hydrogens, and then there's a double bond here, and then there's a carbon with a hydrogen, and then a CH2 like that, and then an oxygen. Whoa, finally finished. See, that took forever. That's the full Lewis structure where you're showing every bond and every atom. So this is the least desirable way of drawing an organic molecule. It's full Lewis structure. Just takes too long, right? And if you recall that molecule of fentanyl, that had a lot more atoms and a lot more bonds. So I would still be writing the structure of fentanyl. Okay, so that's the full Lewis structure. Let me also warn you is that if you have to see every atom and every bond, you're not going to do very well in this course, right? This is the least desirable way of drawing an organic molecule. All right, so there are a couple of other ways. The next way would be the so-called condensed formula. And in the condensed formula, we show every atom. Show every atom, comma, but omit the bonds. Okay, so let's draw the condensed formula of this geraniol. Okay, so we wouldn't draw this carbon-hydrogen bond. We would write CH3, meaning that these 3 hydrogens are bonded to the atom that came before, right? And we know that this doesn't mean CHHHH. We know that's preposterous, right? Because hydrogen never forms 2 bonds and carbon has to form 4 bonds, right? So this CH3 doesn't mean a carbon followed by 3 hydrogens. It means that we have to satisfy the requirements of that valency table where carbon is forming 4 bonds. Okay, so that CH3 is this one. Okay, and now we've come to this carbon here, so that's carbon, right? We're just writing every atom, but we're not writing any of the bonds. And this carbon is bonded to a CH3, but because it's not on this main chain, we have to indicate that somehow, and that is done by writing that CH3 in parentheses. And these parentheses mean that the thing in parentheses is bonded to the item not in parentheses that came before. In the condensed formula, essentially what we're doing is that we are portraying the main chain, right? And the atoms that are in the main chain aren't in parentheses. Okay, so now we have a carbon atom here, then he's bonded to a hydrogen, that's him. And then we have the next carbon atom, and he was bonded to 2 hydrogens, that's him. And then we have another CH2, that's him. And then we have a carbon here, and he's bonded to a CH3 that is off the main chain. So I'm putting him in parentheses to show that he is bonded to this guy that came immediately before. And then we have a CH, and then another CH2, and then finally finishing up with OH. Okay, so that would be, where do I stand? That would be the condensed formula of geraniol. So that took a lot less time to write, but it's not really very convenient because we can't tell what bonds, what are the numbers and kinds of bonds in that structure. So this is a condensed formula. We use this a lot, but probably not to represent a big, huge, complicated molecule. We use maybe little sections. Okay, so that's the condensed formula. We show every atom, but we omit the bonds. All right, so now we are coming to the real iron of the order here, right? This is what we really want to get good at. And this is the so-called line angle, or also I call it the bond line notation. All right, and in this bond line notation, what we do is that carbons exist where lines meet, or at the end of lines, not terminated by another atom. Another feature of this bond line notation is that hydrogens on carbon are not shown, but hydrogens on every other atom must be shown. Okay, and so the geraniol structure, which looks like this, can be represented in this bond angle formula, right? I'm going, just for reference, I'm going to put this here. All right, there's my geraniol, full Lewis. What would the bond line structure look like? Okay, that carbon, this carbon here is this one. It's the end of a line not terminated by another atom. There's a carbon there, and none of the hydrogens are shown there. Their existence is implied, and the number of carbons is, the number of hydrogens must be one of those entries on that valency table, so that this carbon is forming 4 bonds. This carbon up here, he's here. He's at the end of a line segment not terminated by another atom, and he has 3 hydrogens on him, but they are not written. Okay, this carbon, that's a double bond, right? And there's a carbon atom here because we have a carbons where lines meet. And here we have 4 lines meeting. There's a carbon there, and there are no hydrogens there because carbon forms 4 bonds when it's neutral, and I see all 4 bonds. Okay, and so now finishing off the rest of the structure, the bond line formula would look maybe like this. How simple, how elegant, how time saving. So this is what we really want to get good at, drawing these bond line representations. Okay, and so let me just say, we're going to do some problems now, but let me just make some more remarks about the bond line formula. Another thing is that if you ever write a C, comma, you must write the H's that live on that C. Because if you write a C to represent a carbon atom, you're not in a bond line structure anymore. You're either in a condensed format or a full Lewis, right? So if you ever write a C, you have to write all of the hydrogens that live there on that carbon. See, in this bond line formula, I never wrote a C anywhere, so I don't see any H's living on any carbon atom, because this is a bond line formula, not a Lewis structure or a condensed formula. Okay, so let's try to do some problems. Okay, so there's my fentanyl. Okay, milk of amnesia, propofol. Anyone know what propofol is? Anyone know what propofol is? They call it milk of amnesia. Anyone heard of that? Yeah, it's a surgical anesthetic, exactly. And it was, this is what they give you when they're prepping you up for open heart surgery, but also it was something that Michael Jackson had in his system, right? It's also a drug of drug abuse. Copy this structure down and tell me what is its formula. How many carbons, how many hydrogens, how many oxygens? So how many carbons, how many hydrogens, how many oxygens in this formula? Anyone have the answer yet? How many carbons, how many hydrogens, how many oxygens? Okay, let's see what someone says here. "12 carbons is correct. How many hydrogens? 18 hydrogens is correct. How many oxygens? 1 oxygen. Okay. Oh boy, I'm learning. Okay, so here we see this is a so-called mixed notation, right? Because it has elements of a condensed formula, CH3, right? And remember, anytime I write a C, I have to write all the hydrogens that live on that C. So these are condensed formulas, but in here, this is a bond line. So we also have these mixed notations. So how many carbons do we have? 1, 2, there's a carbon there because this is where lines meet. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 carbons, right? How many hydrogens? 3, 6, 9, 12, 13, 14, 15, 16, 17, 18, 18 hydrogens and 1 oxygen. This carbon up here at 2 o'clock doesn't have any hydrogens because carbon forms 4 bonds and I see all 4 of them, right? So this is the kind of structure that you really want to get good at. Let's try another one. C12H18, oh yeah, excellent. Oh, Xanax. Anyone out there? You don't have to respond. Anyone out there on this stuff at the moment? Yeah, you don't have to chime in. I guess it's an antidepressant, right? And this is my beloved Whitney Houston here, who drowned in an inch of water because she was messed up on Xanax. Oh, Whitney Houston, I love her. Copy this molecule down. Tell me what is its formula. How many carbons, how many nitrogens, how many whatevers. So we're just getting practice in interpreting these bond line formulas. That's what we're doing right now. Oh, you know what? I love Whitney Houston. My favorite song of hers is I Will Always Love You. Oh, I just get chills up and down my spine whenever I hear her sing that. I love Whitney Houston. Now, I like to be nice. I'm not nice all the time, but I like to be nice. And I'll just tell you that there are 4 nitrogens and 1 chlorine. Right, so I did you a big, huge favor there. Okay, so what's the formula here? Let's see what people are saying. Oh, someone says 17 carbons, someone says 16 carbons. Hydrogens, well, there are hydrogens, 17 carbons, 16 carbons, 13 hydrogens. All right, so it's a lot of answers out there. Okay, so let's see what we came up with. Carbons. 1, 2, 3, 4, 5, 6, right? Everywhere lines meet, there's a carbon atom there. 6, 6 more down here is 12, 13, 14, 15, 16, 17. Right, 17 carbons. How about hydrogens now? All right, so this carbon here at 10 o'clock, I see 3 bonds. There must be 1 hydrogen there, but hydrogens on carbon are not represented. 1, 2, 3, 4, 5, 6, 7, 8. Nope. 9, 10, 11, 12, 13. So I got 13 hydrogens, right? And in case you were curious, when we write the structure, when we write the formula of an organic molecule, we write carbon first, then hydrogen, and then everything else in alphabetical order, right? That's just something that, that's just a convention. Okay, so let's do some more. I'm going to write a condensed formula, and I would like for you to translate it into a bond line structure. Right, because we have these various ways of writing organic molecules. Let's be able to go between and among all of them. All right, so there's a condensed formula. Draw the bond line structure. So if you're brave, maybe if you know how to share your screen, if you want to hold something up to your camera and let me see it, we could try that. Do you know how to share your screen? Do you want to show me, someone want to show me what they came up with? You're translating this condensed formula into a bond line structure. Any takers out there? Okay. So this carbon has 3 CH3s on it. So this carbon has 3 CH3s on it. 1, 2, 3. Right, this carbon has 3 CH3s on it. And then this, this carbon, we're going to put a little star on him just to keep track. That carbon is this one. And now he's bonded to another carbon, but this carbon with the star doesn't have any hydrogens on it, but carbon forms 4 bonds when it's neutral. So this carbon with the star must be on one end of a triple bond. And this carbon here, maybe I'm going to put a square on him, is this guy, is the carbon that lives here. And he forms 4 bonds, so there must be a bond to the next carbon over. Maybe put a triangle on him. And he has 2 hydrogens on it, but I'm not going to write 2 hydrogens because I'm writing a bond line structure, and I don't never write a hydrogen that lives on a carbon in a bond line structure. And now this carbon with 2 hydrogens, forming 4 bonds, he's off to a nitrogen, right? And I'm going to put an angle in there, right? I'm not just going to draw a straight line. I'm going to put an angle there to make it crystal clear that there's a carbon here. There's the nitrogen. And this nitrogen has two CH2, CH3 groups on it. CH2, CH3, CH2, CH3. So there would be many correct ways of drawing this bond line structure, but that would be a pretty good one. Okay, so let's stop now and try to, today was the first day of school, trying to work all the bugs out. So ask for your patience and try to figure out some of our tech problems. Okay, so you have a discussion at 11:30, but that's all I have for you today. Does anyone want to ask me any questions or anything before we conclude? Any issues about anything? Okay, well, I guess, is the discussion recorded? That is up to the discretion of the discussion leader. How are the quizzes structured? When we get close to a quiz, we'll talk about that. How do you determine the starting position of the first carbon in the bond line notation? Oh, the sapling. Yeah, I have to get that going. I'll get that going at the sapling. I'll get that going, and I'll talk about that tomorrow. Okay, so just addressing this question here, another way that the condensed formula for this very same molecule could be written could be CH3, that's this guy, and then a carbon here, that's this guy, and then that carbon was bonded to two CH3s like this, and then C, so on and so forth. So this would be another way of writing the condensed formula, but you would come up with the very same structure. So I hope that answers that. Okay, so should we go from condensed straight to line and not to the Lewis structure? Definitely. How do you write a condensed formula for a ring? You don't. Mixed notation is acceptable. How do we know how many nodes there are based on the molecule? Antibonding will always have one more node than the bonding. The antibonding won't always have two nodes. The antibonding will always have one more node than the bonding. And I'll tell you about the office hours. Okay, guys. See you tomorrow.